building the sum or dividing two numbers, setting a variable while subtracting a number, negating or dividing logical expressions. All this and much more in today's tutorial video about Golang's operators. Hello and welcome, fellow coders. If you are new to this channel, my name is Thomas and I am on this journey to teach you the Golang programming language. In this video we are going to talk about operators. So what are operators? Operators allow us to perform operations on operands. Well, yeah. Let me give you a quick example. If you add the number 3 to the number 4, the plus sign is the operator, and the 3 and the 4 are the operands. And that is what we are going to talk about today. All these juicy operators that Golang has to offer. If you look at the Golang specifications for operators, you will find a huge wall of text. I'm going to break down all of them in a more easy and digestible way. So let's get started. All operators can be categorized into 5 groups. Actually it is 6 because there is the miscellaneous group. But yeah, we have the arithmetic operators, the relational operators, the logical operators, the bitwise operators, the assignment operators, and lastly the miscellaneous operators that do not fit into any other group. Now let's break them down one by one and start with the arithmetic operators. These are basically mathematical operations that you can perform on any kind of numerical values. Let's for example define two variables called a with the value 7 and b holding the value 2. Now let's print out the sum of both numbers. In this case the plus sign is the operator, acting upon variables a and b. Now let's copy this line so I don't have to type it all the time. Of course, if there's a plus operator, there is also the minus operator, as well as the multiply and the divide operator. If we run the code, we can see that the first 3 lines are pretty self-explanatory. The last line though prints out the result of 3. That is because we assigned our variable with integer values. And in programming, dividing integer values cuts off the precision. Make sure to keep this in mind. There is one more operator that falls into this category, and that is the modulo operator. This operator performs a division, but instead of printing out the result, it prints out the remainder. In our case, that is 1. The modulo operator is oftentimes used to execute actions if something is either even or odd. For example, if you have a table on your web page and you want to highlight every other line. So it's pretty useful. There is actually one special case for the plus operator. It can be used to join two strings together. See, it prints out hello world. And that is it for the arithmetic operators. These are pretty straightforward, right? The next category is the category of relational operators. These are used to compare two values. Let's again take 7 and 2 as an example. To see if a variable holds the same value as another variable, you can use the equals operator. And of course, there is also the not equals operator to check if two variables do not hold the same value. What you can do as well is check if a number is greater or smaller than another number by using these two operators right here. Sometimes though, you run into cases where you want to check if a value is greater or equal than a second number. For that, you can use the greater operator followed by an equal sign. And of course, there's the less than or equal operator as well. Let's run the code and see what the results are. You can see at first glance that all relational operators have boolean values as a result. Obviously, 7 does not equal 2, but the check if 7 does not equal 2 results in the value true. Next, 7 is indeed greater than 2, and the check if 7 is greater than or equal to also yields the result true. Therefore, both lesser checks are false. Now let's see what happens if I change b to 7 as well. This time, the first expression is true and the second is false, which is kind of obvious, right? The interesting part is right here. The greater than or equal, as well as the lesser than or equal expressions, this time both result in true. This will come in handy as soon as we talk about loops. Imagine you have a basket of apples, and you can take out one as long as the amount of apples is greater than or equal to 1, so you don't have to know the actual amount of apples. I know that this is a very simple example, but I hope it makes sense why this operator is so useful. Lastly, I want to show you that all relational operators work on strings as well. If I change a to hello, b to world and run the code, you can see that all these expressions result in the boolean value. Especially the equal and not equal operators are used a lot when comparing string values. Coming up next we have the logical operators. Logical operators combine 2 or more conditions and evaluate their result. Let's take 7 and 2 as a and b again and define 2 conditions. Condition 1, a not equals b, which is true since 7 does not equal 2. And condition 2, a greater than b, which is true since 7 is greater than 2. Now let's combine these 2 conditions using the logical AND operator. The logical AND operator is true only if both operands are true. So if the first condition as well as the second condition both result in true. Let's check if this is actually the case. See, the result is true since both conditions are true. If I change the second condition and check if A is smaller than B, the condition will result in false, which consequently will turn the result of the logical AND operator to false as well. The next operator is the logical OR operator, which results in true if one of the conditions is true. So if you run the code, you can see that the logical OR operator actually returns true, whereas the logical AND operator returns false. If we change the first condition to also be false and run the code again, this time both logical operators return false. The last logical operator is the NOT operator. It returns true if the condition is false and vice versa. Let me give you a quick example. If we print out the results of C1, let me quickly comment out these lines and run it again. We can see that the expression results in false since A does not equal B, but adding the logical NOT operator in front of the expression will now return true. Changing condition 1 to be true will result in false for the logical NOT operator. Pretty simple, right? All these logical operators are pretty important when you write any kind of application. You will use them in so many cases, so make sure to fully understand and memorize them. I would like to encourage you to write your own conditions and play around a bit. Add a third and a fourth condition and see what happens. This will increase your learning tremendously. As for our next operators, we are going to talk about the bitwise operators. To be honest, when writing business logic, you do not use these operators as often as the other ones, if ever. But it still does make sense to quickly go over them. Let's again start with the numbers 7 and 2. For our first bitwise operator, we have the bitwise AND operator. Let's see what the result for the operand 7 and 2 is. Well, that is weird. My computer tells me that the result of the bitwise AND operator of 7 and 2 is actually 2. I think I need a new computer. This one seems to be broken. But hold on, let's quickly go over it why this result actually makes sense. As the name implies, bitwise operators act upon the bit representation of their operands. In binary code, 7 has the value 111. And 2 has the value 10, or rather 010, since you fill up with zeros from the left, and we need both of these representations to have the same length. The bitwise AND operator now goes over every position and performs the AND operator on both bits. For the first position, we have 1 and 0. The AND operator for bits results in 1 only if both bits are 1, which is not the case, so the result is 0. The next two bits are both 1s, so the result is 1. And for the last two bits, the result is 0 again. The final binary result of the bitwise AND operator thus is 010, which is exactly the same binary representation of the number 2. Now the result makes sense, right? The next bitwise operator is the bitwise OR operator, which works the same way as the bitwise AND operator, but instead of performing AND on each bits, it performs the OR operator. Let us again see how this looks like for our numbers 7 and 2. Let me quickly copy and paste this, and let's first go over the result. The OR operator on bits returns 1 if either of the bits is 1 and 0 otherwise. So 1 and 0 is 1, 1 and 1 is 1, and 1 and 0 is again 1. Apparently, the result should be 7. And indeed, 7 it is. The next bitwise operator is the XOR operator. Same as before, the XOR operator performs bitwise operations. This time resulting in 1 if both bits are different and 0 otherwise. 1 and 0 are different numbers, so the result is 1. 1 XOR 1 is 0 and 1 XOR 0 is 1. The result is 101, which is the binary representation of the number 5, which also happens to be the result of the bitwise XOR operator. Next we have the AND NOT operator. As the name implies, it first performs the AND operator followed by the NOT operator, hence turning a 0 into a 1 and a 1 into a 0. Let's again clean up what we do not need. And now we can go over it. 1 and 0 is 0, not 0 is 1. 1 and 1 is 1, not 1 is 0. Again, 1 and 0 is 0, not 0 is 1. So the result should be 5 again, which it actually is. Lastly, we have the left shift and the right shift operators. First, I'm going to explain the left shift operator since the right shift operator is pretty similar. Let's remove everything we do not need and change the operator to the left shift operator. But instead of using 2 as our second operand, let's use 1 first. This will make it a bit clearer how the operator works. The left shift operator shifts the value of the first operand to the left by the number of bits specified by the right operand. This will make more sense if we look at the binary representation of 7 as a byte. 1 byte can hold 8 bits, so 7 can be represented as 4 times 0, 0, 1, 1, 1. You can think of the left shift operator as shifting zeros in from the right to the left, the number of times we defined by our right operand, which is 1 in our case. So we shift 1 0 from the right and let the first bit on the left fall off. This will result in 4 times 0, 1, 1, 1, 0. which is the binary representation of 14. And running the code actually returns 14. Now let's see what happens if we use 2 as our second operand. This will shift in 2 zeros from the right and let the first 2 zeros on the left fall off, resulting in 0001 1100, which is 28. So left shifting 7 once results in 14, which is 7 times 2. Left shifting 7 twice results in 28, which is 7 times 2 times 2. Could this be a coincidence? Well, no. The bitwise left shift operator is the equivalent of multiplying the first operand by 2, the number of times specified by the second operand. Now let's have a look at the bitwise right shift operator. I'm pretty sure you will figure out yourself how this one works. This time we're going to shift in 2 zeros from the left and let the rightmost ones fall off. The final result therefore is 0000 0001, which is the binary representation for 1. Therefore, the bitwise right shift operator is the equivalent of dividing the first operand by 2, the number of times specified by the second operand, always omitting the remainder. So dividing 7 by 2 results in 3, which again divided by 2 results in 1. That is exactly what the computer tells us for the result of the bitwise right shift operator. I know that bitwise operators are a bit confusing, so why did I teach you how they work? Well, there's actually only one reason. If you ever happen to be in a quiz show and the question is if the capital of Germany is either Munich or Berlin, you can say with absolute confidence, well, I don't know. But I know how bitwise operators work. Which will most definitely earn you a lot of fame and laughter. Okay, let's be serious now. I never used any of these bitwise operators because I write code that stores data into databases and represents it in fancy tables or graphs. But if you want to understand how computers work on a fundamental level, you need to know how they operate on bits and bytes. Another thing that comes into my mind is if you write high performance applications. In this case, you probably need these bitwise operators because they are faster. But this might only be an edge case. The next operators I'm going to talk about are the assignment operators. Assignment operators do exactly what they say, they assign something to a variable. You have already used the simplest assignment operator a million times, and that is the simple assignment operator. It simply assigns the right operand to the left operand. Now the value of b is stored in a, so printing out a now gives us the value 2. Let us look at the next one, which is the add assignment. It is the combination of plus and an assignment, so a plus equal b is the equivalent of a equals a plus b. Since a is 7 and b is 2, the add assignment operator takes the sum of both values and stores it into the a variable. See? The value of a is now 9. This is pretty straightforward, right? And the good thing is that all the other assignment operators work the same way, like the subtract assignment, the multiply assignment, the division assignment, the modulus assignment, the bitwise AND assignment, the bitwise OR assignment, and lastly the bitwise XOR assignment. These are all pretty easy, right? Last but not least, we have some other operators that are not falling into any of the above categories. These are the two address operators as well as the receive operator. It does not make sense to talk about these yet, so I will skip them for now. As soon as we talk about pointers, the address operators will be explained. The same goes for the receiver operator. It only makes sense to talk about it while explaining how channels work. Both of these topics will be covered later in the tutorial series. But before we wrap it up, there is one last thing I want to talk about, and that is operator precedence. This means that operators are executed in a specific order where some operators have higher precedence. You can find the order here in the specs of the Golang language. Precedence 5 means that this is the highest, where precedence 1 means that it will be executed last. Operators with the same precedence get executed from left to right. Let me give you a quick example of how this works. If you have a look at this chain of operators, try to figure out what the result will be when printed out. I will give you a few seconds. Do you have your final answer? Okay, let's break it down. In this case, a times b has the highest precedence of 5, so this expression gets executed first. Next are the plus and the minus operators, both with the precedence 4, so they get executed from left to right. So first we add a, then subtract 21, which results in 0. Next the equals operator gets executed since it has the precedence 3, resulting in a false result since 0 clearly does not equal 42. Next the logical AND operator gets executed, which results in false, since false and false still is false. And lastly, with a precedence of 1, the logical OR operator gets executed, resulting in true. Which also is what we get when running our code. And that is it for today. Thank you so much for watching. If you enjoyed this video, you know what to do. And until next time, keep on coding.